Hi, our project is assessing the effect of curing conditions, specimen type, and superabsorbent polymers in compressive strength and abrasion of Pervious concrete. This project was done by Daddino, myself, Cristian Gaedicke, Fadi Castronovo, Saeid Motavalli, and David Ligouri. Why are we interested in Pervious concrete? The answer is stormwater management. In conventional systems, rainwater accumulates on the surface, and also contaminated rainwater ends up in rivers, lakes, and so on. This is why many cities are promoting the use of permeable pavements. And the answer can be seen here on the picture on the right. On top, you can see a conventional pavement that is accumulating water, rainwater, which is basically ending up in the stormwater system. Whereas on the front here, you can see pervious concrete that allows rainwater to go through its section and basically penetrate naturally into the soil. What is pervious concrete? Pervious concrete is similar to conventional concrete with one big difference. It has almost no sand, or in many cases no sand at all. It uses small size coarse aggregates that also are that are of a single size or as close to uniform as possible, and it uses admixtures, and in particular, in this project we're assessing the use of this admixture, which is called superabsorbent polymer. So, in the absence of sand, using a coarse aggregate of a single size or close to a single size, you generate this interconnected network of pores that allow rainwater to flow through the cross-section of this concrete. Why are we interested in superabsorbent polymers? And before we answer that question, an additional question would be, what are superabsorbent polymers? And these ones are materials that can hold up to 1,500 times their weight in water. Okay, so one of the most common uses of superabsorbent polymers is diapers. Why would we use a material that is used for diapers in concrete? And the answer is to enhance internal curing. Internal curing is the process of incorporating a curing agent that serves as an internal reservoir of water and gradually releases that water in the concrete, allowing that concrete to have at the end a higher performance in terms of strength, durability, and so on. This has been done before in high-performance concrete, but there is very limited research in terms of using superabsorbent polymers in pervious concrete. What is our question? Will this will superabsorbent polymers enhance the performance of pervious concrete? To study that question, we develop a couple of project objectives, and basically what we'll try to do is to assess the effectiveness of superabsorbent polymers under harsh conditions. So we'll simulate conditions that are more harsh than laboratory curing, and we'll assess or measure the performance in terms of strength and durability. We'll also control the porosity. Again, our experimental program is summarized in the slide. Basically, you can see pretty much conventional materials that you see in any concrete. Then we have the hydration stabilizer, which is a particular type of admixture. And then we have our superabsorbent polymers. We tried two brands, which we identified as S and SHM. The experimental program is shown below here, and you can see we had 5 mixtures, 1 with a low water cement ratio, and 4 with a water cement ratio that is slightly higher at 0.4. Within this group, we had 1 mixture with no SAP at all, 1 mixture with a low dosage of SAP identified as S, another mixture with a high dosage of the SAP identified as S as well, and finally a mixture with low dosage of superabsorbent polymer identified as HM. You can see the details here on the slide. We prepared each of the 5 mixtures, and what did we extract out of each mixture? We basically extract 6 cylinders that were cast into plastic forms. They were compacted into 2 layers, and each of the layers was compacted using a proctor hammer with 20 drops per layer of the proctoral. Then we did additional 6 cylinders for which we use the same conditions as I described before. What's the difference? That these cylinders over here will be placed in a curing chamber at 85 degrees Fahrenheit, and 68.7% humidity. And the idea of this chamber is to represent what happens in the field. The other 6 cylinders will be placed or will be cured at 70 degrees Fahrenheit underwater. And in addition to that, we'll create 6 cores. You can see the details of the process in the paper, but basically the cores were also cured under field conditions, and they were extracted from a big concrete panel that was created as well. What will we measure? We measure the porosity of each specimen. We'll measure the compressive strength, and we'll also measure the durability. What we'll do for the durability is we'll place 3 half cylinders into this LA abrasion machine, and we'll compare the initial weight of the sample with the final weight of the same sample after 167 revolutions. That variable or that measurement will be identified as ML, or the mass loss. So the higher your mass loss, the lower the durability of your concrete. The experimental results show that the higher the porosity of the specimen, the lower the strength. And you can see this is very well known for Pervious concrete, and you can see that for each of the panels over here in the graph. But what is really interesting is that when we compare cylinders cured under ideal conditions versus cylinders cured under simulated field conditions, is that you lose roughly 34 to 35% of the strength. So this is field and this is the lab, you can see. And when we compare the lab conditions under ideal curing versus the cores cured under field conditions, this loss can be between 27 and 57%. In terms of the use of the SAP, you can see over here that at least for the cylinders that were cast and cured under lab conditions, the SAP created mixtures that had lower porosity, and by extension that generated the concrete that had a higher strength. For durability, we can see the opposite. The higher the porosity, the higher the mass loss, which means the less durable the concrete is. However, cylinders cured under ideal conditions showed far less mass loss with increase of porosity, whereas cylinders cured under field conditions were far more sensitive, and you can see that here on the slope, and for cores it's even worse. You can see that over here. Of course, when you see this, the lab conditions over here versus the field conditions, you can see that overall the mass loss is significantly higher when you have field conditions. You can see this versus this and this versus that. Cores tend to have a higher degree of deterioration, especially at higher levels of porosity. In conclusion, we could see that field curing conditions reduce the strength of cast cylinders by 34 to 35%. This was even more significant for cores, where the loss could range between 27 and 67%. The durability was significantly affected by curing conditions, and you can see that there was a loss of roughly three times the mass loss when compared to specimens cured in the lab under ideal conditions. The preliminary data on SIP indicates that they can give you a material that has a higher degree of workability, which can lead to lower porosity and that can lead to higher strength, but that can also lead to slightly less of a permeability. So more research is needed in that particular area. Any questions?